This is another integral that we are going to solve using trigonometric substitution. And I would just like to iterate in the same video. Basically, if we're given an integral, the very first thing that we have to understand is to see the resemblance, whether the given integral, in this case, the integral of secant squared x dx over quantity 4 minus 10 squared x to the 3 halves. So the first thing that we are going to understand is to see the resemblance of the given integral into each of these three possible forms. In this case, because once you understood the form of this given integral and classify it into case 1, case 2, and case 3, you'll know how to proceed with trigonometric substitution. Now, it's not very apparent, but I'm going to re-express this integral into the other form, and this will become the integral of secant squared x dx, so nothing will change in the numerator. But notice that I can actually rewrite this one as this quantity square root of 2 squared minus 10, say 10x squared, and that's under this square root here. Okay, I cannot write it, that's okay, and to the power of 3. So basically I was able to express this integral into its equivalent form. Now why I did this will become apparent now. Notice that in the form here, we'll try to highlight the form. This section over here, it's not really this one. This form over here, if you notice, is resembling this form here, where our a is given as 2, or our a is 2, and our u is the tan of x. Now, according to this, the trigonometric integration, once you have set what u and a is, you perform this substitution. So what happens now is I'm going to change color, you let u be equal to a sine of theta. So of all the three cases, we are sure that this is case 1, where our a is 2 and our u is the tan of x. Now from here, this tells me that, or this implies that your u, which is, by the way, tan of x, is equal to a sine of theta. Now I'm going to take the derivative both sides. I'll just use that notation. So this will become the derivative of tan of x with respect to x, and the other side would be the derivative of theta. Derivative of a sine theta with respect to theta. So what's going to happen here is I want you to recall your basic differentiation. The derivative of tangent of x is simply secant squared of x dx, and the derivative of the right hand side of a sine theta is simply a cosine theta d theta. I'm going to highlight this portion over here because this is very important later. Now once we have this, we are now going to rewrite everything in our integral. So notice that the portion here, this portion, the secant squared x dx, is actually just a cosine theta d theta. Now in this case, I'm going to be very specific. I haven't noticed this one, but the a here is very specific, as I've said, and that a is actually 2. So this is 2 sine theta. This is 2 sine theta. So the a here is simply being replaced by 2. 2 sine theta, 2 sine theta. Now going back, as I've said, this term secant squared x dx is simply from here 2 cosine theta d theta. So that means to say I can replace the numerator by 2 cosine theta d theta. Now I'm going to deal with the denominator. For the denominator, notice that this will become, that's gonna be 2 squared, because that's going to be a squared minus u squared, minus our u squared is the one that I said I will be highlighting. Based on our trigonometric substitution, that's 2 sine theta. So u will become 2 sine theta, and that is squared. Right? And do not forget that everything is raised to the power of 3. Now, moving on, further simplification, we get, just going to copy this one, 2 cosine theta d theta. The denominator will become, this is 2 squared. I'm going to factor out 2 squared, so this will become, okay, I'm not going to skip steps. So that's going to be 2 squared minus 2 squared sine squared theta, so that you will not get confused, to the power of 3. Now I'm going to simplify this one. This will become, I'm simply rewriting the numerator, and the denominator is, I can simplify it by factoring out 2 squared. So what is left in the radicand is 1 minus the sine squared theta. Now, I think this is already something that you know. You have to recall from algebra that if you have, say, the nth root of a to the n, that will just be equal to a. And that is something that we're going to apply today. And also, you have to remember that the sine squared of theta plus the cosine squared of theta is 1, this identity. This implies that cosine squared of theta is equal to 1 minus sine squared of theta. Now, these are things that we're going to apply. So our integral, nothing will change with our numerator. However, for our denominator, we are going to apply this one, the one I mentioned about the nth root. I mean, taking the nth. Should I call it the square root of some a? So that will become this portion over here, diba? It's understood that you got 2, although it's not written, but you got 2 there. So essentially, what happens there is this one will be applied. This one. Okay, this rule will apply. So what happens is 2 will get out of the radicand. So you have 2, and then the square root of. So everything will just be, after taking out 2, 1 minus sine squared of theta. But what is sine squared of theta? You know from here that this 1 minus sine squared of theta is simply cosine squared of theta. So that means to say that our integral will look like this. 2 cosine theta d theta. And then we get 2 square root of cosine squared theta. Alright. Okay, I actually missed something here. I'm going to correct myself. I forgot that everything is actually raised to the power of 3, so be careful in doing that. This is raised to the power of 3, and this is raised to the power of 3. So from here, notice that we apply the same thing over here. On the square root of cosine squared theta, you can apply this one. The nth root of a to the n is a. So how does that apply here? That will make the expression equal to 2, and that will just be cosine theta. And then raised to the power of 3. Now, further simplification, we got 2 cosine theta d theta. And then this is 2 to the cube cosine cube theta. Right? I'm hoping you still follow. Now in this case, we can simplify this one. So 2 will cancel out, so this will become 2 to the 2. 1 cosine from the numerator will cancel out, so that will be just cosine squared. So what is left in our integral is now a simpler form of d theta. That's what is left in the numerator. In the denominator, you get 2 to the square, or 4, and then you get cosine squared theta. I'm going to take out the constant, the 1/4 out of the integral, so I get d theta over cosine squared theta. So I'm now getting a very simple expression for my integral. Now, recall, I'm hoping you can recall this one. 1 over cosine theta is actually, I'm hoping you can recall, secant theta. So that means to say that our integral can be further re-expressed as the integral of secant squared theta, d theta. Now I'm hoping you get to understand why we did this, because you need to recall also that the integral of secant squared, secant squared theta, d theta, is very simple, and that is just the tangent of theta plus c. Now that means to say that this integral now can be expressed as 1/4 of the tangent theta plus c. But then again, we still have the question, what is tan of theta? So we have to express tan of theta in another form that makes sense in our problem. Now, how do we do that? Recall, I've mentioned earlier that this one is very important, and this is where it gets its relevance. Now, you let u to be 2 sine theta, right? So, u is 2 sine theta. What does this imply? This implies that sine of theta is equal to u over 2. Now, I'm hoping you do remember that sine of theta is opposite over the hypotenuse with respect to the angle. Now, this will be important because we're going to do some geometry over here. Trigonometry. We will do some right triangles. Now, if this is your angle theta, arbitrarily your angle theta, according to your to u is equal to 2 sine theta, this tells you that the opposite would be u over 2. But what is u? We know that u earlier is, based on our expression, u is actually the tan of x. So this is tan of x all over 2. Now, sine of this angle theta over here is opposite over hypotenuse. The opposite part is this one. This is the opposite with respect to that angle, and that is the tan of x. And then 2 is the hypotenuse. So if this is your 90 degrees, this is your hypotenuse, and this part here is simply 4 minus tan squared x. Now, if you wonder why that is 4 minus tan squared x, you simply use the Pythagorean theorem to do that. But I'm not going to look into the details because it's very basic. So now we're going to express, as I've said, the tan theta into something that is the original variables, which are in x. So how do we do that? We do that by understanding that the tangent, I'm going to use a different color, the tangent of, say, blue. The tangent of theta is simply, if you can recall, opposite all over the adjacent of this angle over here. Now, that means to say the opposite of this angle theta, the opposite of this one is this, the tan of x. So you write here the tan of x, and then the adjacent with respect to this angle over here is this term over here, square root of 4 minus tan squared x. So you get square root of 4 minus tangent squared x. Okay, Right. So that's your tan theta. So you're going to substitute that here because your integral is originally in terms of the variable x. So it doesn't make sense if you're getting some theta over there. So we have to revert back to the original variables which are in x. So this tan of theta, it turns out that this tan of theta is simply this one. So you're just going to rewrite this as tan of x all over the square root of 4 minus tan squared x and plus c. And this is how you do trigonometric substitution for this integral over there. It actually looks very complicated at first sight, but once you actually follow through the process of trigonometric substitution, integration by trigonometric substitution, you do realize that it actually simplifies.